Okay, good, good, good. Okay, today is lecture number 2, and so we're going to continue from last time. So today we are going to look at a few topics. Okay, number 1, the topic is the Gaussian elimination. Okay, you can also follow the lectures by reading the textbook. Okay, I think we are still in chapter 2 on this textbook. So the first topic today is going to be about Gaussian elimination, and then second one is about matrix decomposition. So actually, a matrix can be decomposed in several ways, but today we are going to look at a decomposition called A equals to L multiplied with U, where L is a lower triangular matrix from last time. Then we can decompose into L multiplied with D or diagonal matrix, and then multiply with an upper triangular matrix as well. Okay, so this one is going to be a unique decomposition. For A equal to L multiply with U, it's not unique, okay, but for LDW it's gonna be unique. Okay, so basically these are two topics we're going to talk about today. So let me go with the first topic number 1. Okay. So what are we going to do? So let me give you an example of a set of linear equations. Okay, let's say that we have linear equation as follow. Let's say we have 3 linear equations that we are trying to solve. Okay, say that the first equation I call E1. Okay, this is the 2x minus 4y plus 6z. Okay, equal to 18. Okay, then we have equation number 2. Okay, if you don't hear me well today, please tell me, okay? Because I'm talking with tablet today. It's not like usual. So for equation 2, let's say we have minus 3x plus 9y equal to minus 12. And equation 3, let's say that we have 2x minus 5y plus 5z equal to 17. Okay. So for this type of equations, so let me ask some of you, if you need to solve for x, y, and z, how are you going to solve this? X, y, and z, so they are unknowns in this case. Okay. So what are the conventional way of solving for this type of equations? Well, if you remember, anyone has an idea, can you share? Tanat, Tirawit, for example. Tanat Son, you have any idea how to solve this type of equations? If you need to solve for the unknowns, x, y, and z, okay?
Eliminate any parameters.
Say again?
Eliminate any parameters.
Okay, so that's one way of doing it, okay? So in order to solve this type of equations, you can, okay, to solve this equation, okay? So the different ways to do it, you can, well, eliminate some of the variables, right? So that's one way. Okay. Secondly, you can also do some types of matrix form, like a matrix form of this equation. Okay. So you can notice that in this case, how many equations are there? We have 3 equations, right, for 3 unknowns. So a general rule of thumb is if you have 3 unknowns and you want to solve this type of equations, you need to have at least 3 equations. Okay. So in general, when we have, say we have n unknown, yeah, my writing is gonna be because I'm not so good with writing on tablet. Let me do it this way. Okay, maybe it's better. So let's say we have m unknown. In general, okay, we need at least n equations. Okay. If you have, if there are less than n equations, okay, sometimes it's not solvable. Okay. So in order to solve this type of equations, set of equations, we need to understand about, all these type of different criteria as well. Okay. So today I'm going to, so let's take a look first, for example, in terms of matrix form. Okay. So if you look at matrix form in general, okay, I can write these 3 equations as follow. So what I can do is I can set x, y, and z as a vector, like unknown vectors, okay, and then multiply it with the coefficients from the 3 equations. For example, if I look at equation number 1 here, if I look at equation number 1, I notice that these are the coefficients that are multiplied to the unknowns, which are x, y, and z. Okay, so I can write these coefficients 2, minus 4, and 6 on the left hand side. Okay, so I can write minus 2, 4, and 6 on the left hand side, and then I can set it for the first equation. I can set it equal to the number on the right hand side, which is 80. Okay. Well, similarly, for the coefficients of the second and the third equations, I can write minus 3, 9, 0, and also 2, minus 5, and 5, respectively. And for the values on the right hand side, I can just write it like this. Okay. So generally for matrix form, the way we write it as A multiplied with an unknown vectors. Let's say in this case I put X, okay, and here let me call it as a B. And in this case, because the matrix A has a dimension of n by n, which is a square matrix, and it is actually 3 by 3. Okay, so
Sorry.
yes,
Screen not update.
say again.
The screen not update.
The screen does not update. I see. Okay.
Yes, yes.
Has it updated? Has it updated yet?
Yeah.
No.
No. Okay, let me take a look. Yeah, sometimes that happens. One moment. Maybe I can do it this way. Okay. Okay, let me try to do it this way. One moment. Let me change the router briefly. Can you hear me well? Okay. No? Oh, yes. Okay. So let me go back to the screen again. What do you see now? Maybe I can check from another computer just to make sure. Oh, you're right. It doesn't. Okay. Okay, let me share the screen one more time. Okay, a moment. Stop presenting. And then share screen again. Okay. Yeah, please tell me today. I suspect it's going to be a very strange day today. Okay. So where were you earlier?
At in unknown.
Were you here? In unknown here, right? Is okay. So were you on this line earlier?
Yeah.
Okay. 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 Good. 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 Let me use another computer. Make sure that I can see like the same screen as you do. Okay. Okay. So what I'm saying here is that okay, good, good, good. So what I was saying here is that so in general, you know, when you have an unknown, you need at least n equations in order to solve such a system. If you have less than n equations, in general, is unsolvable. Okay, except in some cases, and we will see more criteria or conditions later as we go on. Okay, so if I start by looking at this type of matrix form, okay, so I can put all the three equations above, you know, in this matrix form. Okay, so I can write the unknown as x, y, z like this, and call it a vector x, so that okay, as an unknown vector. I call this unknown vector. Okay, and then for the left hand side, this is the coefficient matrix. Okay. So if I go back to the equation, let's say equation number 1, okay. Okay. I noticed that this is equation number 1, and these are the coefficients that multiply with the unknowns, which are 2, -4, and then 6. Okay, and the right hand side is equal to 18. So in terms of in a matrix form, I can put -2, 4, and 6 right here on the first line. Okay, because when I put a and x like this, it means that -2 is going to be multiplied with x, 4 is going to be multiplied with y, and 6 is going to be multiplied with Z. Okay, so the multiplication of the first row and the first column together indicates the first equation, and it is equal to AT. So similarly, I can put the coefficients of the second equation, which are -3, 9, and 0, so that they will multiply with the column of X, Y, and Z, and is equal to -12. Okay. And similarly, for the coefficients of the third equation, when it is multiplied with the unknown vectors, it's going to give you the value of 17. Okay. And so what happens here is that, so in general, you know, in this case, because A, which is the coefficient matrix, it has the dimension of a 3 by 3, which is a square matrix. Okay. So if you can write the equation as AX equal to B like this, how do you think we can solve it in general? If we want, so we can solve the X matrix equals to what? Well, I can just multiply A inverse, right, to the left-hand side of A and X. Okay, so I get X is equal to A inverse and then multiply with B. Okay, so I mean that's one way of doing it. Alternatively, if A is a matrix with the dimension of M multiplied with N, which is not square matrix, okay, and I multiply it with the N, with the unknown vector, which is X vector with the dimension of N multiplied with N multiplied with 1, okay, then I get B, which is M multiplied with 1. Okay. In this case, I cannot just do an inverse. Okay. Cannot compute X is equal to A inverse B. Okay, because the A is not a square matrix in this case. Okay. So in general, if A is not a square matrix like this, one approach that we have to do is we have to do this. We change to the blue colors. Do you know? Can you suggest what we can do if we given A multiplied with X equal to B, but A is not a square matrix? You have any ideas? You think? Fill with.
Low operation.
Say again. Say again.
Low operation.
Row operation, which is what? To switch between rows, or what? Or something else? What do you mean by row operation? Well, the word row operation is quite generic. It's a little bit difficult to understand what it means exactly. How about Thanatson? You have any idea? If we are given AX equal to B and A is not a square matrix, what can we do to solve for X? Any idea, Thanatson?
No.
No? Okay. Okay, anyway, if anyone has an idea, you can raise your hand and then tell me now. Okay. Okay, if not, I'm going to show what one way of doing it. So we have AX is equal to B, but because A is not a square matrix, so we cannot find the inverse of A. One approach is to do this, to multiply A with A transpose. Okay, so if you do the A transpose, what is the dimension of A transpose? Pure.
Yes.
Yeah. If I multiply with A transpose, which is here, what is the dimension of A transpose? If A is M by N, what is A transpose?
N by M. N
So
by
it's
M.
just switch number of column and number of row, right? Okay.
Yes.
So you notice that these two multiplication, the dimension will become N by N, which is a square matrix. Okay. So what we can do is then we can just say that X is equal to an inverse of A transpose multiplied with A inverse and multiply with B. Okay. Oh, sorry. When I multiply A transpose to equation 1, on the right hand side here, I need A transpose as well. So it means that I need to have A transpose multiplied with B. Okay. So this is one way of computing. Okay, but there's a problem with this type of operation. It's not that you cannot do it, but when n is very large, if n is large, meaning that you have many unknowns. When I'm talking about a large number of unknowns, let's talk about like 1,000 or 1 million. Okay, so when n is large, the operation of inverse is quite how do you call it? It's quite power intensive. Okay, it is quite complex, and so on. Okay, so we don't want to do the traditional inverse because it's very costly, it's very power intensive, and also very complex. Okay, maybe you remember that one way to do inverse is to use the Cramer's rule. Okay, so this is one technique based on the cofactor, and it has the complexity of like n factorials. You know, so let's say that n is equal to 1,000 variable. The complexity of this case is the n factorial, which is 1,000 factorial, which is very large. Yeah. So I mean, it's not always convenient. We can write it in terms of analysis, but in terms of really solving the equation, you know, if n is large, then we don't want to do this inverse operation. Okay. So we come to the Gaussian elimination. I remember that when I started, one of you, maybe was it Tanat, right? Did you say that we will do some type of elimination, right?
Cherwit said that.
Say who said that? Tirawit? Was it Tirawit who says that? Okay. Anyway, so now we will look at what is called Gaussian elimination, which is a technique that tries to help decompose the A matrix so that it is a bit easier to do inverse. Okay, so for the matrix A, which is large, like n by n, or even m by n. Okay, so we will try to decompose. Okay, and so that it is easier to find inverse than the traditional approach of computing inverse of A. Okay, so that's what we are going to do. So okay, so let's start from writing the three equation again. Here, because I have tablet, if my screen is not so large and it's very strange to write equation, just tell me, okay? Okay. So we're gonna start like this. Let me start from, say, it's the, okay, like this. Let's say it's called step I, okay? We have the first equation, which is 2x minus 4y plus 6z equals to 18. Okay? And for equation 2, we have minus 3x plus 9y equals to minus 12. And then equation 3, we have 2x minus 5y plus 5z equals to 17. Okay. So these are just the equation that we wrote earlier. Okay. So we have three equations, and what we are going to do is we are going to do some elimination, okay, by converting, by adding or subtracting each equation, one equation from another, so that we have equations that have one or two or three variables. So what we are going to do here is we will try to eliminate some variables from this equation, okay, so that we have equations with one unknown, two unknowns, all the way to, and then three unknowns, okay? So that's what we will do. Okay, so what do we do? Here we have three equations. So what we are going to do is we are going to leave, because we need the equation with one unknown, two unknowns, and three unknowns, okay? So just for an example, let me write it as step 2, okay? I'm going to fix the first equation to have three unknowns. So they will be fixed as in the step I, okay? And then for equation 2, I'm trying to reduce the unknowns so that they have two unknowns. And then for equation 3, I will try to reduce so that we have just one unknown, okay? So for one unknown, we will try to play with equation 3. For two unknown, we play with equation 2. And for three unknown, I just fix it as equation 1. Okay, you can switch around. You can do whatever you want to. Okay, so let's first let's look at equation 2. Okay, from here, equation 2. Okay, now in this equation 2, we have three unknowns, which are x, y, and then z. Okay, we have two unknowns already. But when we make two unknowns, we are going to eliminate the unknown of x, okay? Or you can do separately. But in this case, I'm trying to, so for the three unknowns, I have x, y, z. For two unknowns, I'm gonna reduce them to have just y and z. And for one unknown, I'm gonna reduce to have just z, okay? So for equation 2, if you take a look at the step I, first I'm going to try to eliminate x out of equation 2. Okay, so what can I do to do that? Basically, one way I can do is I can add equation. I can add equation 2 with equation 1 multiplied by 3/2. Okay. So what I'm going to do is I'm going to add equation 2 with 3/2. But instead of adding 3/2, I'm going to write it as minus 3/2 equation 1. Okay. And let me write this as equation 2 dash to signify that it's changed from equation 2. Okay. So if we do this, what are we going to have? So we're going to have the first term will disappear. So this will be like 0. Okay. You can jot it outside. Okay. Maybe I can jot it outside at the top so that you can see. So for x, I have minus 3x. Okay. And then plus 3/2 of 2x. So this will be minus 3x plus 3x equal to 0. Okay. Then for the next term here, okay, I have 9y and then plus 3/2 of E1, equation 1, which is minus 4y. Okay, this will be equal to 9y minus 6y, okay, which is equal to 3y. So in the modified equation 2, I'm going to write as plus 3y. Okay, and similarly for the last one, I have 0z, and I add it with 3/2 of 6, so I get 9. So I get 9z, which is equal to what last one. So I add minus 12 with the 3/2 of 18, which is 27. Okay, so I get minus 12 plus 27, which is 15. Okay. Well, we can do similarly for the equation number 3. For the rule of thumb is when we do equation 3, we also try to eliminate. The unknown x first as well. Okay, so maybe we can do this together now. Okay, so for equation 3, if I want to eliminate 2x from E1, or if I want to eliminate EX 2x from E3, okay, so I will start with E3 and then I minus 1 times E1, okay, and I call this E3 dash, okay. So can you do together with me? So the first term, I have a 2x minus 2x, which is 0. How about the next term? Thananpat, can you tell me what's the next term is? So the next term, I just have minus 5y and then minus this term.
Minus 9.
Actually, it's minus 5 and then minus 4, which is
Yes.
plus 4. Okay, so I'm gonna get minus y instead here. Let me write as the blue colors. Okay.
Yes.
Yeah. So I get minus y here. Or let me erase it so that it's a bit easy to see. Okay? And next, this one is plus 3. Okay. How about the next term? So next term I have plus 5z and then plus E1. Okay. So what do I get Theodore with?
minus 4.
So here we have 5z and then plus 6z, right? Oh, sorry, minus 6z. So we get, you said minus z? Okay. So we have minus z here, okay? Equal to what? Okay, please do one
minus
more.
1.
So you get minus 1, yes. So this is the step number 2, okay? And so when we do this, so the next step, let me draw a line so that it's a bit easier to see. Okay. Yeah, unfortunately, my tablet is quite small, so the screen is not large. Okay. Okay. So next, so you can see that during the first step, if I go back up here, during the first step, I have 3 equations, right? First, I have 2 equations. So I operate the eliminations on 2 equations. Okay. And okay. So this step, for this step, I have now I have 2 equations that I want. Oh no! I mean like this. During the first step, I have 3 equations. So I do operation on these 2 equations. Okay. So these are the 2 equations that I operate in order to eliminate the variables. Okay. So for this step, I have 2 equations. So in the next step, I have to operate on 1 equation, which is equation number 3. So we operate on 1 equation, which is equation 3, E3 prime. Okay. So let me write down step 3. Okay. Equation 1 is still left as before, which is 2x minus 4y plus 6z equals to 18. Okay. And then we have equation number 2 prime, which is left as it is, which is 3y plus 9z equals to 15. Okay. And then we have equation 3. Okay. So here we are going to try to eliminate y from equation E3 prime. Okay. So what do we do? In this case, because we have E3 prime and also E2 prime. Okay. So we are going to eliminate the variable y in E3 prime from E2 prime. Okay, so we're going to eliminate. We set up E3 prime, and then if we want to eliminate this y from E3 prime, okay, I'm gonna set E3 prime first, and then I'm going to add 1/3 to E2 prime, okay, to get the new equation 3. Let me call the new equation as E3 double prime, okay. So we have to start from first term, okay. So the first term is 0, okay. 0 plus 1/3. 0 plus 1/3 of 0, I just get 0, so I get nothing, okay. And then for the second term, I have minus y plus 1/3 3y. So here I have a 0, which is nothing. Okay. And then for this term, I have minus z and then plus 1/3 of 9z, okay. So here, what do I get? I get 3, and then 3. So I get 2z. So here I just write down 2z, okay, and equals to 15 plus 1/3 18, which is 15 plus 6, okay. Oh, sorry, no, it's the -1 and then plus 1/3 18, okay. So here I have -1. Oh, sorry, -1 plus 1/3 15, or 1/3 of 15. So I have -1 plus 5, okay, which is 4. So here I write as 4, okay. I go a little bit slow, but I hope that you follow what I'm doing. Okay. So here we have 3 steps, okay. And after this, what we can do is then we can go to the second part. So the first part that we do, all this equation, I can call it as the elimination step. Elimination step. Okay. And then when we finish all the way down here, then we can do the part that is called substitution. Substitution step. Okay. Well, the reason we can do this is because here we have one variable, which is 2z equals to 4. If we can find the value of z, then we can substitute z into the equation e2 prime to get y. And then we can substitute y and z into equation 1 to get x. Okay, so that's what we are going to do. Okay, so for the first step, I get z. This is very easy. So z is equal to 4/2, which is 2. Okay. And then from equation e2 prime, then this one is from equation e3 prime, double prime. Okay. Let me write it together. And then from equation 2 prime, then I get what? I get y is equal to 15 minus 9z divided by 3, which is 15 minus 9 times 2 divided by 3. So what do I get? Pio, what do I get here?
-1.
So I get -1, okay. And finally, so here we have the value of z, the value of y, okay. So we substitute the value of y and z back into equation e1 prime, okay. Or not e1 prime, just e1, because we haven't changed anything. So from e1, then we have that x is going to be equal to 18 plus 4y minus 6z and everything divided by 2. Okay. So here I have what? Hanatson, what do I have here? Oh, he's not here. It's okay.
1.
Yes. Again. What do you
1.
get? 1.
1.
Okay. So basically it's 18 plus the 4, which is -4, right? And then -6 times 2 and divided by 2, okay? Which is 18 minus 16 divided by 2, which is 1. So from this process, therefore, the solution x is equal to 1. and then y is equal to -1, and then z is equal to 2. Okay. So here we have two steps that we work, which is the elimination of unknown from the equation step, and then followed by the substitution step. Let me see whether you can see the screen well or not. I noticed something very strange. Okay, you can see it. Okay. Additionally, when we were doing these steps for the elimination, okay, I can write for each step, like step 1 to 2, I can write these numbers as the number here as the multiplication coefficients, okay? And generally what we can do is we can write the multiplication coefficient as with the index of the first equation minus the second equation. So here we can write the coefficient as m21, which define the order of equation 2 followed by equation 1, and it is equal to -3/2. And also, in order to convert or transform from equation 3 to a new equation, the coefficients of the multiplication is called m31, which is 3 and 1, and it is equal to 1. Okay. And for from step 2 to step 3, similarly, we can write the the multiplication coefficient as m32 is equal to -1/3. Okay. So these are the coefficients to combine the sub-equations in order to get the new equation to reduce the number of unknowns. Okay. So here below we can say that for the elimination steps, we have the multiplication coefficients. In order to reduce unknowns as followed, we have m21, which is -3/3. We have and then m31, which is 1, and then m32, which is -1/3. Okay. So this is Gaussian elimination. And well, so when we compute when we solve the equation this way, so how is the complexity compared to just Cramer's rule? Okay, so let's compute the complexity. Okay, for a lot of you who works on algorithm, very often you will have to evaluate your algorithms in terms of complexity. Okay, and in this case, I'm going to look the complexity in terms of the number of operation count. Okay, and here I will look at the operation count of multiplication only. Okay. Of course, when we do operation count like this, which indicates a complexity, it may not necessarily refer to the complexity in hardware. if you work on the hardware operation and you try to come up with the complexity, oftentimes they have to consider some other parameters as well. Okay, so in this case, it's more like the complexity of the algorithms that we are looking at. And the reason we look at the multiplication more is because the multiplication in general takes more resources compared to the summation. Okay, so let's take a look. So the complexity consists of two parts. The first part is the complexity in doing the Gaussian elimination. Okay, so for this part, what do we do? Well, we are given with the n equations, okay, and n unknown, okay, from the previous examples. We have n equation and n unknown, and in particular, from our example, n is equal to 3, okay. So what's the number of multiplication that we do? Okay, so if you remember when we were looking at up here, okay, let me use the maybe orange, green colors, okay. So during these steps, from step 1 to step 2, okay, from step 1 to step 2, well, if we have 3 equations, we need to work on 2 equations, okay. And what do? We work on 2 equations, and for each equations, what do? We multiply constant value. We multiply the constant value to each of the coefficients of the unknown, and also the solution on the right hand side. Okay. Okay. So it means that from step 1 to step 2, we work on for 3 equations. We work on 2 equations only, and for each equation we have to multiply. We have to do multiplication 4 times. Okay. So it means that in general, so we start from n equations. We start from n minus 1 equations. Okay. That we have to do the eliminations. The number of equations to do elimination. Okay. And for each equation, we have to do multiplication n plus 1 time. Okay, multiplication. Okay, so that's the first from step 1 to step 2. Okay, so this is from step, I think on previous page we say from step I to step 2. Okay, and then from step 2 to step 3, okay. So now instead of having 2 equations to work with, we only work with 1 equations. Okay, so we work with 1 less equations. Okay, but the multiplications, because it's still the same number of coefficients and the output, so we multiply with n plus 1. Okay, so this number of multiplications, and this is the number of equations that we have to work with. Okay, On the previous example, because we only have 3 equations at the start, so we only do 2 equations and then 1 equation and then one we finish. Okay. But in general, what we need to do is, so starting from okay, so basically we have to work with from 3 equations to 2 equations, right? And then from 2 equations to 1 equation. Yes. Okay. So we have to sum this up all the way to all the way to 2 equations. Okay. Okay. Therefore, it means that the total operations in this case is going to be equal to n plus 1 multiplied with n minus 1 from above plus n plus 1 multiply with n minus 2, right? And plus all the way to n plus 1 multiply with 2. Okay, so this is total number of operation in terms of multiplication. Okay? So the first term, we can write this as n square minus 1. Okay. Okay, second term, we can write it as n plus 2 multiply with, well, we can write it like this, n plus 2 minus 1 multiply with n minus 2, okay, which is equal to n plus 2 times n minus 2, okay. Wait, I think there's a formula like this. I want to reduce it like this, sorry. I want to reduce it to okay, I want to reduce it like this. Sorry, let me do it this way. Okay, because this term is n square minus 1. So I'm gonna try to write this as n minus 1 square. Okay, and then so these terms will come here, and this term will signify this. So this one is n square minus 2n plus 1, right? But up here, this is n square minus this. This is the n square minus 2n, right? Minus 2n plus n, and then minus 2. Okay. Let me see. Does it add up? N square minus 2n plus n, and then minus 2. This is n minus 1, n minus 2, n square minus 2n plus 1, right? So if I write n square minus 2n plus n minus 2, so I can write n square minus 2n plus 1, okay, and plus n minus n minus 3, right? Let's see. Well, it doesn't add up like what I wanted to. One moment. Did I do anything wrong here? I'm just trying to factor the terms. The first term looks correct, right? N square minus 1. Okay. Then the second term, this is n plus 1 minus 1. Plus 1 and plus 1 minus 3 and minus 3. Okay, let's take a break. I'll come back. I think some numbers don't add up. They're supposed to look a little bit cleaner than this. Okay, give me 5 minutes. Give me 10 minutes. Okay, let's take a quick break. We'll come back.
Okay.
Okay. Something doesn't add up. One moment. Okay, let's come back. Previously, I made some mistake. Let us go back to this page. Let me show slide again. Present screen. Okay. Okay, you can see now, right? Okay, so let us go back to this step. So earlier we were trying to compute the number of operations for the Gaussian elimination step, right here. Okay, so for n unknown and also n unknown and unknowns and then equations. So from step 1 to step 2, here we have n unknowns. Okay. And then we have n equations. So we only work with n-1 equations. Okay, we fix the first equations, but for the remaining equations, which are n-1 equations, we try to eliminate one unknown. Okay, so these are the n-1 equation that we try to do elimination for one unknown. Okay, and in our example, this unknown is x. So in order to do that, we have to multiply the weighting or the coefficients to all the unknowns, which are n unknowns, plus one, what is it? One component of the b, plus one more value. Okay. So therefore, the multiplication here is the n plus 1 times. Okay. So that's the first step is okay. Then from the second step to the third step, here we have only n-1 unknowns, n-1 equations left. Okay. So we only work with n-2 equations. Okay. And then for multiplication, because we only have n-1 unknown. Okay. So including one value, which is the output, the rightmost value. Therefore, we only have n multiplications. Okay. So this will continue until the end. So if I go to next step, I'll do next step as well. If I have the next step from step 3 to step 4, for example, okay, then I will have n-3, and then multiply with n-1. Okay. So you see that each number that are multiplied to each other, okay, they're reduced by 1 always. Okay. And this goes all the way to the last step. Okay. So we can write it like this. In this case, we can write it as n plus 1 multiplied with n minus 1. And then the next step is n multiplied with n minus 2 plus n minus 1 times n minus 3. Okay. And this goes all the way to the last steps. Okay, so this is how we will compute. So you notice that for this term, we have n square minus 1. Okay, and then we add it with the next term, which is n square minus 2. Okay, but this n square minus 2, this is n square minus 2 minus 2n. Okay, so I will try to express it as n minus 1 square. So I add 1 and then subtract 1. Okay, so here I will have this term, something like this, you know. So this is like how we try to work on. Okay, and we'll do this for next term. Let's say this is the next term. Next term is n square minus 4n, and then plus 3. Okay, so I try to express it as n minus 2 square and then minus 1, because this is n square minus 4n plus 4 and then minus 1. Okay, so I'll keep doing this until the end, and the last term here is going to be 2 square minus 1. Okay, meaning that the last step we only need 3 operations. Okay, so we can write that the total number of operations, okay, we can write it as summation of k square minus 1, where k is equal to 2 all the way to n. Okay, wait, is it n? Yeah, okay, I use small n, no? Okay, and in order to express in terms of n, I will will expand this in terms of k square for k equals to 2 all the way to the n, and minus summation of k equals to 2 to the n and then 1. Okay, okay. Oh, I see. Also, because for the term where k is equal to 1, I get k square minus 1 equal to 0. Okay, so here I can express as k equals to 1 to n and then k square minus 1. Okay, this is because if k is equal to 1, this term is 0 anyway, so they are equal. So in this case, I can put the beginning of k from 1 to n instead of 2 to n, just for simplicity. Okay, and from here, then I can use the formula for the summation. Okay, for the back term, this is easy. You just add up from you add up 1 n times. Okay, so here you get n. But for the front, we can use the summation formula for variable square. So we get n multiplied with n plus 1, multiplied with 2n plus 1, divided by 6. Okay. So this is the formula for summation. Okay. And then, well, so what is this equal to? We don't need to precisely, when we evaluate the complexity, we don't need to precisely evaluate each variable n, because here we will notice that the front terms, it has multiple of n, so it's the like exponential. So this exponential term will dominate, okay, dominates the back term, okay. So this term will dominate this term. So we can say that the complexity we can put in terms of the more dominant term as 2n cubed divided by 6, okay, which is equal to n cubed divided by 3, okay, where n is the number of equations, which is the size of the matrix A. Okay. So that's the first part for Gaussian elimination. Okay, sorry for taking such a long time. You know, I haven't done it for some time, so I got a bit confused as well. And then the next step is the complexity for the substitution. So I put 2. So next is the complexity for the substitution part. Okay. For the substitution part, the number operation, we work from the bottom equations to the top, right? So for the first equation, if you take a look back at the step here, okay. So during the substitution, what we do is like this. We start from the bottommost equations, okay. Because here we only have one variable, so we do the division or multiplication just one time, which is here. Okay. So here we just do this the multiplication of 4 with 1/2. Okay. Actually, it's division, but for complexity purposes, multiplication and division, they are the same. So they're comparable. So we can just say that. So here we have 1 time of multiplication. And then for the second equations here we have 2 times of multiplications. And then for the last equations, we have 3 times equations, okay? So if we have n equations, we have to do the multiplication from 1 time, 2 times, all the way to n times, okay? So in this case, we can say that, so in this case, we say that during the substitution part, the number of operation is equals to 1 plus 2 plus 3 all the way to n. Okay. And this is, we can use the formula for summation of k is equals to 1 all the way to n, okay, which is n multiplied with n plus 1 divided by 2, which is n squared over 2 plus n over 2, okay. And similarly, because this term dominates the second term, so we can say that the operation count is around n squared over 2, okay. So so then the total complexity or the total number of operation from the two steps, okay, from the Gaussian elimination and also from the back substitution, this is equal to n cubed over 3, and then plus this term, which is n squared over 2. I think it's n cubed over 3, no, sorry. N cubed over 3. Okay. So we can say that I would use approximately, because we take away some terms for both parts. And because this is n cubed, so the first term, which is n cubed, also dominates the second terms. Okay. Imagine if n is large, okay, then when you take to the power of 3, then it dominates the term with take to the power of 2. Okay. So here we can say that the complexity of the solving equation like this is around n cubed over 3. Okay. And then in terms of, in general, in terms of complexity, we often use what is called O factor. Okay. O factor is a way to approximate the operation complexity by taking into account of the largest power without the how do you call it? Without the weighting terms or coefficients term. Without the weighting terms. And in this case, the weighting term is in this case is 1/3. Okay. So here we will say that therefore the complexity of this operation is O factor. We write it as an O, like a it's the writing of the alphabet, and then we take away the weighting term, which is 1/3, so we write this 1 cubed. Okay. And this is how we compare complexity in general. Okay. So for example, if we do the comparison between such a linear equation solution between the traditional methods like Cramer's rule and Gaussian elimination. So we can compare Cramer's rule, okay, which versus the Gaussian elimination method. Okay. Okay. For Gaussian elimination, as previously mentioned, the complexity is in terms of n plus 1 factorials. And for the Gaussian elimination plus back substitution we saw earlier, the complexity is n cubed over 3. Okay. So let's say that for each n we can compute some of them, right? So let's say that n is equal to 2. Okay, let's try it. N equals to 3, n equals to 5, n equals to 10, n equals to 20. Let's say there are 20 unknown, no? And we'll see what's the comparison between these two methods. Okay. So if I do n equals to 2, what is the complexity? Theodore Witt Okay, so for n equals to 3, we have a 3 factorial. Okay,
6,
again,
6,
3 factorial is, let me have a note, jot note here. 3. Okay, so 2 plus 1 factorials is 3 factorial, which is 3 times 2 times 1, no? Okay.
yes,
So what do we get? We get
6,
8? No. We get 6. Okay. So this is 6. Okay. How about this? What do we get here on the right hand side? So we have 2 cubed over 3. So what do we have here? What is 2 cubed? 2 to the power of 3.
x divided by 3,
So it's 8 by 3, right? Okay. How about next, n equal to 3? What do we have, Sanat?
Yes.
So what do we have for n equals to 3? What is the complexity?
24.
Yeah, so it's 3 plus 1 factorial, which is 4 factorial, which is 4 by 3 multiplied by 2, blah, 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 right? So you get 24. So this is 24, okay? How about on the right-hand side?
9.
9. Okay, yeah, okay, so it's the 3 cubed divided by 3, which is 3 square, right? Okay, so it's 9. Okay, I think my eye is getting blurred from looking at the tablet for 2 hours. My God. Next, okay, for next one maybe a bit more difficult. If n is equal to 5, which means we have 5 unknowns. So here we have 722, right? If you don't agree with this, please tell me, no? And then here I have 42. If this is the n equals to 10, I have 11 factorial, which is about 4 times 10 to the 7. And then if here we have 10 cubed, which is 1000 divided by 3, which is 33. Okay. Now if n is equal to 20, now it's getting difficult. Okay. You can try it yourself at home. Okay. So you can see that when the number of unknowns increase, if you still use the inverse method based on Cramer's rule, for example, then the complexity is very high compared to the Gaussian elimination. I think Gaussian elimination, the complexity is more like a linear. It's not linear, but it's very low compared to the Cramer's rule approach. Okay. Okay. So this is the first part, which is Gaussian elimination. Okay. So the next topic that we are going to look at is about matrix decomposition. So we will use the result from doing Gaussian elimination to look at the matrix decomposition. Why do we need to do composition? Well, there are various benefits of doing the decomposition. Okay, and well, one way is to help reduce the complexity in terms of computing the complexity of equation solving. Okay, but and for some other benefits for decomposition, you can use it for some other processing. Instead of processing the pure matrix, you can decompose it first, and then you can process the smaller elements in the matrix. Okay. So if I first go back to the equation that we were looking at earlier, okay, we set up AX equals to B like that, right? And we write matrix A, which is 2, minus 4, and then 6, minus 3, 9, 0, 2, minus 5, and 5, okay? And for the unknown, they are X, Y, and Z, which is equal to 18, minus 12, and 17, okay? So what we can do is we can decompose, or you can say factor, no? We can factorize matrix A and write it in terms of the multiplication of L multiplied with U, where L is the lower triangular matrix from last time, and U is the upper triangular matrix from last time. And in particular, for matrix A, we can separate into L and U, multiply to each other, okay? For the L matrix can be constructed with the elements, okay? For the lower triangular matrix, which is L, here we have 3 by 3, and U also 3 by 3, okay? So for the elements above the diagonal line, we have all 0, okay? Because it is lower triangular matrix, okay? And for lower triangular matrix here, at the diagonal, we have a 1, 1, okay? And then for the elements here, 1, 2, 3, okay? This is, so we have this one as L21, L31, and L32, okay? So how can they be constructed? Because of the way we reuse the equations, so we write L21 is equal to M21 from previously, the coefficients for transforming the equations. So we have minus 2, 3 half, and L31 and L32, they are equal to the coefficients from the equation manipulation that we did. Okay, so this will be M31 and M32, etc., which is equal to 1 and then minus 1/3. So in essence, matrix L can be constructed from the coefficients from the Gaussian eliminations. Okay, so let me write down here. So matrix L is constructed from Gaussian elimination. Okay, so that's what we do. Okay, so it means that I can write these values as the computed coefficients, which is minus 3 half, 1, and then minus 1/3. Okay, so this is L. Okay, and then we multiply with the U. Okay, so how can we compute U? So let me come down here. I'll come back up. Okay. So we have A equals to L multiplied with U, like that. Okay. So in order to get U, what we do is Let me write to the right so that it's a bit easy to find. So we have A equals to L multiplied with U. Okay. So what we can do is we can multiply to the front of A with the we call it the elementary matrix. Okay. Which this L, so we will multiply with E21, E31, and then E32. Okay. And each elementary matrices, they come from the coefficients that we looked earlier. Okay. But the coefficients here, they will slightly change. For example, E21. So for E21, this is the elementary matrix with diagonal as 1. It's still lower triangular matrix, okay, with the value at index 21 as the M21, but we will put the negative to it, and the rest is just the same. Okay. For E31, it's also the same, lower triangular matrix, and then at the index 31, we put the negative of the coefficients. Okay, so here maybe you put some colors here so you don't get confused. And then lastly, for E32, which is the elementary matrix for for equation transformation. So we have 1, 1, 1, 0, 0, 0, and then M2, we have a 1/3. Okay. So it turns out that if we multiply A with all these elementary matrices from we will get to U. Okay. And we can write this as A is equal to E32 inverse, E31 inverse, and E21 inverse multiply with U. And each of these term, yeah, this is very interesting. Each of these term is just the inverse of these elementary matrix. Okay, they are the same, just a different sign. Of E21, sorry, so it's minus 3201, and E31, which is here, and then 101, and last one is 111, 0, 0, 0, 0, 0, and then minus 1/3. And this is U. So basically, so these are the metrics from the equation transformation coefficients. Okay. Okay. And if we multiply them together, we will get the matrix L. Okay. If you don't believe, you can try. So that means that therefore matrix U you can compute from E32 times E31 and then times 21 and matrix A. Okay. And if you multiply this with matrix A, okay, you will get matrix U as 2 minus 4, 6, Okay, and 3 and 2, 9, and then 0, 0, 0. And you will notice that the elements here are almost the same as the A matrix, but not exactly. Okay, so if you compare with the matrix A here, okay, so this term is the same, this term is the same, this is the same, and yeah, that's all. But some other terms not the same. Okay. And here in this case, because we set the diagonal matrix for matrix L as 1, 1, 1, so U becomes accordingly. Okay. And okay, so if I go back to here, that means we can, when using the Gaussian elimination, we can decompose A into L multiplied with U. Okay. But in MATLAB, if you use MATLAB, you can use the command called LU. You can just do like this, LU equals to LU and then matrix A. Okay. But if you take a look up here, the way we multiply A equals to L times U here. Okay. If we don't define what L is, then there are many combinations of L multiplied with U. Okay. So in MATLAB, you may not get the same results as doing that multiplication. Also, you may not get the same result as what we did earlier. You may get a different pair of L and U. Also, when you do the Gaussian elimination, if you have some row operation like row switching, and then you do the Gaussian elimination, you may get different L and U as well. Okay, so what is needed to note here is that this decomposition is not unique. Okay. Okay, so lastly about this equation processing, equation solving. Okay, we can write because up here we transform the Gaussian elimination. Let me go back briefly. We try. Oh, sorry, I go back very far. We do the Gaussian elimination, right? And at this step, so we transform the original equations into these equations. Okay. So we can write the equation in terms of L and U like this. Okay. So from Ax is equal to B. Okay. Because we can decompose or factorize A to L multiplied with U, and then X is equal to B. Okay. If we consider these as C, then we have L multiplied with C equals to B. Okay. And and ux is equal to c. Okay. And if we use the result from the Gaussian elimination above, okay, this C is the value that we have after the Gaussian elimination in equation number 3. Okay, so if you look back, this C is here. I go back, sorry, a bit further. Okay, so this is what we have. And here, so this equation is the same as u multiply with x is equal to c. Okay, so Gaussian elimination is, in a way, it is the way of decompose matrix A, so that the final stage here we have ux equal to c. Okay, and u is just 2, 4, minus 4, 6, 3, 9, 2. So the coefficients of the last stage, okay, you can just read them out from the Gaussian elimination. Okay. Okay. So matrix U that I showed earlier, matrix U here, okay, they can come from the coefficients at the last stage of computation. Okay. And when you do a lot of this, the equation transformation is like multiplying the original matrix A with the elementary matrix, depending on how many times you do the manipulation. So in this equation, what you do is you convert the equation A x equal to b into ux is equal to c. Okay. And this is from the last stage that I showed earlier. And this u is just 2 minus 4, 6, 0, 3, 9, 0, 0, 2 multiplied with x, y, z equals to 18, 15, 4. Okay. And after substitution, what you get is x, y, z is equal to 1 minus 1 and then 2. So this is the Gaussian elimination. Okay, a little bit more. In addition, sometimes you will find that when you do ax is equal to b, sometimes it's easier to rotate some rows. Okay. Okay. Sometimes it is easier to switch the rows in the matrix A first. Okay. So in that case, what we do is we multiply A with a permutation matrix. So we'll get PAX equals to PB. Okay. And then after the Gaussian elimination, okay, so we convert PA into L times U and times X. Okay. So then we can proceed the same process. Okay. And here, this P multiplied with A is the row exchange. Okay. Row exchange of A. For example, if you have, let's see, let's say earlier you have A is equal to, let me see, A is 2 minus 4, and then 6, and then you have 3, 9, 0, 2 minus 5, and then 5, right? If you multiply with permutation matrix, say 1, 0, 0, 0, 0, 1, and 0, 1, 0, okay? So what you get here is you are switching between row 2s and row 3s. You get 2 minus 4, 6, 2 minus 5, 5, and then 3, 9, zeros. So sometimes when you do Gaussian elimination, we need to do such switching as well. This week I'm going to start to give homework already. So the homework is probably due within 2 weeks. So you can try doing all this. But the Gaussian elimination and also this type of LU decomposition is one of the very basic. As we go on more, we will decompose or factorize the matrix A into many more types of decomposition for usage. Okay. And lastly, before we leave, let me stop with this interesting approach. Okay. So this decomposition LU, A is equal to LU, okay? If I can decompose A is equal to LU, how can I find an inverse? An inverse is just U inverse multiplied with L inverse, okay? And it's quite simple because the L inverse is the same as L, except that the element of the diagonal axis or the diagonal lines are reversed from positive to negative, okay? For example, if L is equal to 1, 1, 1, 0, 0, 0, and earlier we have M32 of minus 1, 3, right? Let me write as a red colors, so it's a bit easy to see. Minus 1/3, okay? So this is this minus 1/3 is the element, the non-zero element. Okay? So if we find L inverse, we will just have 1, 0, 0, 0, 1, 0, 0. And then 1/3. That's all. So it's very simple to find the inverse as well. Okay. If there are more terms that are not zeros, okay, you can just change the sign of all the elements that are not at the diagonal lines. So it's quite simple to do this, okay? And the matrix U inverse can be found similarly, okay? Okay, so I guess I'm gonna stop here. But before I stop, let me stop sharing this page, and let me go to the MATLAB screen quickly to show some step for you. Okay, so let me share from another screen instead. Okay, so let me share from. Also, let me turn off the camera. If I share from the whole screen, maybe, okay. And I go to MATLAB, okay. This is an example, okay. Okay. So you can see how it works and how it's done, okay. Let's say that I have A as this matrix, okay, which is the same matrix as we looked at earlier, okay. And I already mentioned that if we compute the LU factorization in MATLAB, the way the thing is in MATLAB, what they do is they reorder the diagonal elements, so we don't get the same results. Okay, if you do it like this, you will get L and U like this. Okay, which is not particularly the same as the what we have. Okay. But and also in our case, our L is all one here because the way we do Gaussian elimination. Okay, but here they do it differently, and so they get different U, but both work fine. Okay, so that's one way, and the other one is okay. So here, if you look at this L, and if I want to find the inverse, okay. I just do inverse of L. Okay, let me do inverse of U. No, it's the same thing. So it's maybe I'll do both. Okay, inverse of L. Oh, let me do L again one more time first. So it's on the same page. Okay, let me put this up. Okay, so this is L. No, if I do inverse of L, what do I get? But this L is different, I think. This is not a lower triangular matrix, right? Yeah, in MATLAB, I think they do LU a bit differently. So maybe let me try to show from the example that we looked at earlier. Okay, let me do it again. L is, let me try from the example that we looked at earlier, which is 1 0 0 0 1 0 and 0. Well, it's minus 1/3 and then 1. Okay, but minus 1/3, I think they will evaluate the matrix for you. Okay, and if I find the inverse of L, okay, so see, I have the same thing, but this term is inverse, is the change from negative to positive value. Okay. So if we express matrix A as L multiplied with U like this, it's going to be very convenient to do some inverse computation, and so on. Okay. So next time we will come back and continue and do more decomposition of A. Okay. So we'll do a lot of decomposition of matrix because it's very useful and helpful. Okay. Another useful another useful approach like this is we'll talk next time. Yeah, they have different utilization that important. I think even like Facebook, when they have all these parameters that come in, all the time, and they want to make computation, they also factorize the matrix as well. Okay, so let me stop here for the composition. Next lecture we'll come back and take a look at it. Okay, yeah. Well, I didn't think that it's gonna take this long today, but unfortunately. Does anyone have any questions? Let me stop presenting. Also, Thananpat, can you stop the recording as well? ช่วยหยุดอัดให้ด้วยเนาะ Okay. Yeah, I guess I think unfortunately